Hi, and thank you for viewing this presentation. My name is Dave Bobella. I'm the Director of R&D at TrueNano. We're a company that develops manufacturing equipment and processes that enable low-cost production of device-grade silicon carbide. This material is a key component of high-efficiency power electronics that the Navy views as essential for current and next-generation warfare platforms like the Triton, Zumwalt, and laser weapon system shown here. When the Navy asks, how can we make this smaller, lighter, go farther, or use less energy? The answer is usually designing the system with silicon carbide power electronics. The problem is that these switches are still far more expensive with respect to silicon-based switches that dominate the market. That has a lot to do with how the thin device layers of silicon carbide are made. These epi layers need to come down in price. As such, the Navy has asked us to reduce the cost of these materials by developing new ways to produce these epi layers. We stepped up to this challenge and developed a prototype manufacturing tool and process that delivers a 50% reduction in these costs, increases their throughput, and has a lower cost of ownership. Our tool is first of its kind. It's versatile and scalable to high volume production. It lowers the Navy's costs of using these superior materials for their next generation fleet, and it enhances the national defense by securing a US-based manufacturing know-how. This talk will take you through our manufacturing technology as it relates to silicon carbide power switches. But at TrueNano, we have the expertise and capabilities to produce silicon carbide layers suited for other applications. Think heat spreading wafers, optical windows, and coatings for harsh environments. As you listen to these next slides, keep these in mind and try and think of applications where these layers might be advantageous to use. Email us your thoughts and opinions. Let's discuss how our technology can meet your needs. Let's talk about TrueNano. We're a small business that believes silicon carbide power switches will play a role in revolutionizing the world. We believe that developing a U.S. manufacturing base with know-how and intellectual property is essential for achieving a stable supply chain for these materials that will eventually be in every electric vehicle and power switch. We've been in this business since 2005, being active both in the R&D and tech commercialization spaces. We're silicon carbide growth and device experts. We've been involved in successful startups and have advanced the knowledge base through academic publications. Throughout the years, the DoD has chosen us for other projects to develop silicon carbide power switches, and now it chose us to make the material that makes these switches. We're working to unlock silicon carbide's full potential, first by attacking the problem of high manufacturing costs. That's the goal of this project. And second, by developing yet to be commercialized cubic silicon carbide technology. This tech has the potential to make even more efficient switches for electric vehicle applications than what is currently available, and it can be an inexpensive platform for RF gallium nitride devices. It's an exciting technology. The manufacturing technology we developed here is one of a kind and lowers the costs of production. And what's more, we're the only company to make this work. This differentiated technology is a value prop for U.S. semiconductor tool manufacturers looking to get into the big business of silicon carbide growth. To the Navy and the DoD, the advantages of silicon carbide power electronics are a no-brainer. They have consistently called for innovation in this field, over 65 times in the past few decades. If you read the old solicitations, two themes emerge. One is that these power switches reduce size, weight, and cost of power controllers and increase their energy efficiency. These attributes are compelling for platforms like unmanned aircraft, vertical takeoff and landing aircraft, and directed energy weaponry. This persistence has paid off too. Through consistent investment in this device development, the advantages are now being realized. The second theme you hear is that costs are still too high. While it is true, making silicon carbide is still just more expensive than silicon, some progress has been made to lower costs using conventional techniques that were perfected for the silicon industry. There is, after all, a big and growing silicon carbide device market. But there's plenty of room to improve, and we believe the opportunity is best met through novel manufacturing tools that make silicon carbide layers faster and cheaper. To put all this into perspective, here's an example of what success means to us. Our manufacturing methods reduce costs of producing silicon carbide Epi-Wafers. These are the wafers with device layers on them. The cost reductions translate to cheaper costs of highly efficient switches, which eventually make their way into power controllers that are smaller, lighter, and more efficient. At the system level, the improved swap metrics translate to longer range, higher payload, increased troop capacity, or increased lethality. In this scenario, the Navy advances their strategic goals, and we advance the US-based silicon carbide ecosystem. It's a win-win. From an operational and improvement perspective, the advantages of silicon carbide power switches are easily seen when you look at advancements made in power controllers aboard electric vehicles. Toyota, for example, did a head-to-head comparison of performance from a power control unit made from all silicon power switches and one made from all silicon carbide power switches. Through the combination of higher efficiency and higher switching speed, designers were able to eliminate active cooling loops and shrink the passive components like capacitors and inductors. The result? A power control that's 4 times smaller, lighter, uses energy more efficiently, and is less complex. You can see where this is going. Using controllers that waste less energy and are smaller and lighter gives the vehicle more range, payload capacity, or the ability to achieve some other strategic metric. From this, it is easy to see why the Navy wants to advance the state of the art for making silicon carbide more cost-effective. Let's drill down into the manufacturing tool we developed over the past 2 years. This tool uses TrueNano's hot filament chemical vapor deposition technology to grow epi layers of silicon carbide. Think of it as a high-tech toaster oven. Inside the hot oven, gas molecules that contain silicon and carbon are forced to flow through an array of white-hot filaments. This is the key ingredient that differentiates our technology from other deposition techniques. The filaments condition the gas, which makes it possible for a layer of silicon carbide to grow when those gases hit a substrate beneath the array. That's the essence of the technique in a nutshell. The devil, of course, is in the oven design and the nuanced process conditions that are part of our corporate knowledge. In terms of reducing epi-wafer costs, we've shown that this design scales easily. Right now, we can grow on 4-inch wafers, and it's easy to configure the system for growing on 6-inch wafers, the current industry standard, and ultimately on 8-inch wafers, where the industry is heading. We've tuned the growth recipes to maximize throughput. And importantly, we've lowered the cost of owning the tool by reducing the amount of wasted consumables compared to other tools. There's a bonus too. We designed the chamber to be modular. It can be combined with other chambers in a cluster configuration where many chambers are run independently but are serviced by a central robot. This makes it cheaper to expand capacity or grow non-standard layers. Instead of buying another $2 million machine, you simply add a single chamber for a fifth of the price. Lastly, I want to bring this to your attention. Our technique can be applied to other material systems for applications like coatings or semiconductor growth. For example, with a simple change in process conditions, this system can be used for crystalline diamond growth or diamond-like coatings. If you're not sure whether our technology can help you, please email us. This project started in a Phase 1 effort in 2018 at a tech readiness level of 2. During this period, we did a deep dive into the material properties of epi layers we grew and also a deep dive into the reactor design. From this work, we proved there were no fundamental barriers for using this technique to grow device-grade epi layers. On the business end, we developed a cost model that estimates epi layer costs in low and high volume manufacturing scenarios. This exercise was highly useful. It revealed key cost drivers, and knowing these, we were able to tailor the process and furnace design to reduce their impact on the epi layer cost. In Phase 2, we further refined the design by CAD modeling the tool and then simulating the flow and thermal transport during process. Through this iterative design-redesign process, we finalized a prototype that met certain process specs like temperature, flow, and pressure. Then the real fun began. We built, calibrated, and tested the system to verify its functionality. We mapped the process space and re-verified the material quality. In these final months of the option period, we're demonstrating the scalability by growing over larger areas. We're also making devices from our own material as a final proof point of our material quality. Carrying this technology to market requires transition funding and strategic partnerships. In short, we need to transform our lab prototype into a highly reliable, polished tool that we can use and that we can sell into a competitive market. We need partnerships in the semiconductor manufacturing space that can provide this level of engineering expertise and validation of our epi layers. If that person is you, or there's someone that comes to mind who we should talk to, please email us. I'd like to now describe the advantages that our novel process lends over traditional CVD methods that currently dominate the semiconductor manufacturing space. From conversations with our colleagues in the business, we hear time and time again that low cost of ownership and high material throughput are the metrics that sell a technology. You do this by lowering cost of consumables and increasing the material growth rate. So how does our solution stack up? Well, first, by design, the single wafer growth system uses nearly all the expensive gas consumables for growth. Very little is wasted. We do this by forcing the gases over the wafer, and we minimize the hot surface area where gases may deposit and be wasted. Compared to competitors, which rely on batch mode and planetary designs, our process lowers gas consumable costs by 50%, and that has a direct impact on the bottom line. Secondly, our system uses hot filaments, the key differentiator, to actively condition gases before they hit the wafer, which does not happen in traditional CVD processes. This distinction may seem subtle, but it results in a 2x increase in how fast the layers grow when all other conditions are kept equal. That's a big deal. It means the tool throughput can be 2 times higher than the competition. And since our design is a single wafer system, it is compact and less complex. It has a smaller footprint on your manufacturing floor. It's cheaper to build and cheaper to maintain. It's no coincidence that we're developing tools for the silicon carbide power electronics industry. The market is already big and showing enormous growth potential. Here's a bird's eye view of the market with data provided by Yole Development, who are experts in analyzing semiconductor sectors. In general, the market derives strength from the growing electric vehicle, photovoltaics, and EV charging markets, who view silicon carbide as the semiconductor of choice for their power inverters, converters, and onboard charging units. The EV market makes up the lion's share of the total, which is expected to grow to about $2.5 billion by 2025. That's up 30% CAGR from 2019. This upstream demand for these power devices has to be met by the entire downstream supply chain, from the device manufacturers all the way down to the Epi-Wafer suppliers where we exist. For demand to be met, there must be manufacturing tools to make those Epi-Wafers. So let's look at an example of the market opportunity for the tools we would sell and focus just on the opportunity created by EV market pull. By 2025, global EV sales are expected to approach about 10 million cars. But let's take a cautious estimate and say that 1 million EVs actually make it into production. Inside each EV, there are about 1 to 2 Epi-Wafers worth of silicon carbide power devices. Prices of these Epi-Wafers are around $1,000 each, making for about $1 billion wafer demand. We back calculated the number of Epi-Wafer production tools needed to meet this demand and found that the industry needs about 1,000 of them. These tools typically run well over $1 million each. So when you finish the math, you see there's about $1 billion opportunity for production tools from this segment alone. But if you need more proof that the opportunity is real, consider this. Manufacturing giants like SiCrystal and Wolfspeed, among others, are trying to stay ahead of the curve by investing billions of dollars to increase their wafer and device capacity. This is certainly good news for tool manufacturers that supply those companies with tools to fill their fabs. Before concluding, I'd like to describe the business model we're pursuing. There are two inroads for producing revenue. The first path is to use our production tool and process to produce Epi-Wafers ourselves and then sell those directly to device customers. This approach leverages our existing resources to make first sales. It's a low-volume business and one that uses our process flexibility to fill orders for the niche market of non-standard device layers. It is by no means optimal, but it is the fastest path to a revenue stream. The second inroad is to become the production tool supplier and sell our tool and process directly to device manufacturers that have their own in-house growth capabilities. This approach is more ideal than the first, but comes with a higher barrier to entry. There's a good reason for this. Device manufacturers tend to have strong relationships with their equipment suppliers. But if asked to choose between the status quo and our tool that lowers their epi layer cost by 50%, increases their throughput, and is cheaper to own, they may be open to a change. Getting to the second business model will require additional resources. We anticipate a $5 million investment over 2 to 3 years will give us the runway to transform the prototype into a highly reliable production tool. Part of this investment will go towards building two types of strategic partnerships. First, we need industry partners that are experts in semiconductor manufacturing and that are looking for either an entry point into the silicon carbide market or looking to expand their portfolio. And second, since nobody is going to take a chance on an unknown quantity, we need partners that are willing to test our silicon carbide in their devices. This will establish credibility that our tool, process, and material are the real deal. Specifically in the Navy, we want to hear from program managers that need higher efficiency devices for their platforms. And we want to hear from engineers designing with silicon carbide. Think programs that have electric platforms like the Electric Ships Office, unmanned aircraft, and the Naval Research Lab. Are there device structures or coatings that are hard to source? Is there a new silicon carbide application that you're testing? If the answer is yes, or even a I'm not sure, let's have a conversation. Please email us. On behalf of TrueNano, I'd like to thank you for your attention. In this talk, I laid out our manufacturing tool for producing low-cost silicon carbide Epi-Wafers and how it adds value to the Navy's strategic goals. Along the way, I asked for your help in identifying applications, transition opportunities, and strategic partners. Were you able to think of any? Or maybe you have a question about how our technology can meet your needs. In either case, please email or call us to schedule a virtual meeting. We'd love to discuss your ideas. Thank you.